Okay, Assalamu alaikum all. So, to begin with, let's have a look at an example, which is handling the single effect evaporation system. The example basically is about a single effect system designed with the following information: that bulk stream temperature, the brine temperature is 75 degrees Celsius. The brine salinity is 75,000 ppm, whereas the salinity of the feed is 45,000 ppm. The intake seawater temperature is 28. Steam temperature is 95 Celsius. The distillate quantity which is expected is 1 kilogram per second. And the feed seawater temperature, T feed, is supposed to be 70 degrees Celsius. Then some additional information like boiling point elevation. It's given as 1 degree centigrade. Sometimes it's not given. Sometimes the boiling point elevation is to be calculated, and the calculations can be done either through providing a polynomial, like an equation that you can substitute in it. That's a function of the temperature and get the boiling point elevation. Or temperature, a function of temperature and salinity. Or you can get it from engineering equation solver as a built-in property. The overall heat transfer coefficient in the evaporator is 2.5 kilowatt per meter square centigrade or Kelvin. Overall heat transfer coefficient in the condenser is 2 kilowatt, again, per meter square centigrade or Kelvin. And the latent heat of evaporation or condensation for the vapor, it is 2324 kilojoule per kilogram, whereas HFG for steam, latent heat for the condensation, is 2260 kilojoule per kilogram. So this is the kind of data that is available for this problem. And so this is given information. And what we need to calculate basically is what is essentially the PR, performance ratio. I will jump on the Q and just ask for area of the evaporator, area of the condenser, and m dot cooling water. This is typically what would be asked for such a case or such kind of problems. We know that the unit is made up of two components: a condenser and an evaporator. In the condenser, we know what's coming in is basically m dot feed and m dot cooling water. They are going to be heated from T cooling water up to TF. And then m dot cooling water will be returned to the sea, whereas the feed is going to be sprayed here, which is m dot feed. Part of it will evaporate, and the rest is going to be rejected as rejected brine. Then we have basically, we can say that we have steam coming from the power plant. It will flow inside the tubes. So we have m dot steam at T steam, which is going in a saturated vapor, and it will leave out a saturated liquid. The kind of analysis that we would do for this problem is that we start by mass balance. And for the mass balance, we'd write the equations m dot feed is equal to m dot distillate plus m dot brine, and the m distillate is the same as m dot vapor. And m dot feed, x feed, is equal to m dot brine, x brine. This is because x of the distillate is 0, and this is the assumption that we do, that the distillate is free of salt. Now we have the m dot distillate, the value is given as 1. We don't know the feed and the brine. And then we have m dot feed is not known. X feed is given, which is basically 45,000. And X brine is given, which is 75,000. Which means that from here we can establish a relation between the feed and the brine flow rates. For example, m dot brine is nothing but m dot feed, x feed over x b. We take this m dot brine and we substitute it here. When we do that, you'll find that we have one equation and one unknown. The unknown will be m dot feed because the distillate is known as 1. Then feed, it's the same parameter, and the ratio over xf over xb can be obtained from here. Solving the two equations together can get us the values of m dot feed as 2.5 kilogram per second, and for sure m dot brine is m dot feed minus m dot distillate, so it's going to be 1.5 kilogram per second. So this is the first thing that we need to know for this analysis, which is how much is the feed flow rate, because the feed flow rate is a part of the energy balance for the evaporator. Having done that, we'll get to the calculations of the heat transfer rate in the evaporator. So now we know the feed flow rate and we know that brine flow rate. So when we apply the equation for the energy balance, in the evaporator, then Q in the evaporator is, remember that what we use here, we use the source of heat is the steam, and the steam is going to enter as saturated vapor and it will leave saturated liquid. So the kind of energy transferred here is HFG of steam. So m dot steam into HFG steam is the quantity of heat released by the steam to condense from saturated vapor to saturated liquid. This energy will be utilized to heat the feed from TF to TB. Sorry. And evaporate some vapor. So all the feed has entered here. It will all of it flow on the horizontal surface of the tube bundle, And then part of it, all of it is going to be heated to the saturation temperature. In addition, part of it is going to evaporate. We have a mist eliminator here so that it would make sure that whatever is leaving is pure vapor, and any droplets of the brine are going to fall down again at the bottom so that it would be rejected. M dot feed is known now, which is 2.5. CP should have been given, and for salty water, a value of 3.8 is a good approximation. Kilojoule per kilogram Kelvin. So CP is 3.8, temperature difference, TB is 75, TF is 70, plus M dot vapor is equal to 1, and HFG of the vapor is 2324. From here, we can calculate the value of QE as 2371.5 kilowatt. This specific quantity is equal to M dot steam into HFG of steam, which is 2260. And from this, we know that M dot steam is 1.05 kilogram per second. It's a simple energy balance. And now we can determine the value of the performance ratio PR, which is M dot distillate over M dot steam. The distillate is 1, the steam is 1.05, so the value here is 0.96 or 97, something like that. So this is the first requirement here, which is the performance ratio. We're still in the analysis of the evaporator, and what I'm going to do is basically continue with the energy balance, but we need to involve the area. We are interested in the area. This is QE, by the way. So I'm going to keep this value, which is QE, that is 2371.5 kilowatt which is equal to the overall heat transfer coefficient in the evaporator, area of the evaporator into delta T. Overall heat transfer coefficient in the evaporator is provided as 2.5, area is unknown, and delta T simply is T steam, which is 95, so this is T steam minus TB. T steam is 95 and TB is 75. From here, we can calculate the area of the evaporator, which is, in our case, is going to be 47.4 meters square. Note that when we are doing that, we assumed a constant temperature difference, which is basically, we are talking about conditions of steam as the hot fluid, which is constant, and the vapor also is at a constant temperature. So when you are looking at, say that we need to talk about how the temperature variation is happening here, talking about temperature versus distance, steam is condensing at a constant temperature, and vapor is evaporating at constant temperature as well. We did, the seawater. So this is T steam. It's condensing from saturated vapor to saturated liquid, constant temperature. And here the vapor also is saturated. It has reached the saturation condition. The quantity here of increase of temperature from TF to TB, we are going to consider that this area is too small and it will be neglected. assuming here that we have heated the feed to saturation temperature and it will remain at saturation temperature. That's why here we considered the temperature as a constant temperature difference between the two fluids, steam and the brine or the seawater, which is actually sprayed on the outer surface of the tubes. If you want to be accurate, if you want to be meticulous, then you are going to say that, no, I'm going to split the area to two parts. This is one part of it. And the second part has to take care of this kind of constant temperature of the steam, whereas the feed is being heated from TF to TB, and then you are going to calculate an overall heat, you're going to calculate a log mean temperature difference and can calculate the area which is associated with this small part. But believe me, it's too small compared to the total area. Then you may safely neglect it. Not all the cases we are going to do that, but this is a case where we can say, yes, it's not a bad approximation. Now, we also know what's the value of A of the evaporator. Then we are going to shift into the condenser. And for the condenser, let me clear this. Alhamdulillah. Sorry. So it's the condenser, okay. For the condenser, Q condenser is equal to m dot vapor, which is m dot distillate, into HFG vapor. The vapor that came here as saturated vapor, it's going to condense to liquid, which is our product, m dot distillate as liquid. So it has gone through a change of phase from saturated vapor to saturated liquid. So this is 1 into HFGV is 2, 3, 2, 4. So it's 2, 3, 2, 4 kilowatts. Then the temperature profile here is going to be different because I'm going to have this is the vapor temperature, which is TB nihilus boiling point elevation. The boiling point elevation is given to be 1 degree centigrade here. And this is going to be utilized to heat the feed from T cooling water up to T feed. So this quantity that we have here, and basically when you look at the analysis here, we have m dot feed plus m dot cooling water. So this is going to be used to heat m dot feed plus m dot cooling water into Cp into T feed minus T cooling water. When you look at this equation, what's the unknown here? What is it that we don't know in this equation? Any opinions? Ya shabab, did you sleep already?
T feed, I think. T feed, right?
It is. What we don't know actually is TCW is given, actually it's given as 28 degrees centigrade. This is the seawater temperature.
Yes,
And TF is known because it's given here. It was written somewhere here. What we don't know is this quantity, how much of this. We know the m dot feed, but m dot feed alone is not enough to condense all the vapor. We need additional water. So some water will come in here to help in making sure that all the vapor will condense, and then this water will be thrown away back to the to the sea. So it's the m dot cooling water that we don't know. We know m dot feed, we know Cp, we know T feed, we know T cooling W, and we have already calculated QC. So from here, you are going to calculate m dot cooling water, and this quantity will be calculated. Let me see, do I have it here with me or not? I'm not sure about this. Yes, 14.56 kilogram per second. Wow, this is a substantial amount. Remember, the m dot feed is only 2.5 kilogram per second, but you needed seawater of another almost 15 kilogram per second coming with it just to take care of energy rejection, to take care of the fact that we should make sure that all the vapor which is coming is supposed to condense. QC also is equal to the overall heat transfer coefficient in the condenser, area of the condenser into the log mean temperature difference for the condenser. Now this we are going to say that here we have delta T1, we have delta T2, so that delta T1 is T vapor minus Tf, delta T2 is T vapor minus T cooling water, so that the log mean temperature difference is delta T1 minus delta T2 divided by ln delta T1 over delta T2. And the log mean temperature difference, when you calculate it for this system, you'll find that it's equal to 17 degrees centigrade. From here, we know the log mean temperature difference, we calculated it. UC is given, the value is something like 2 kilowatt per meter square centigrade. Q condenser is known, so the only unknown here becomes area of the condenser that can be calculated, and the area of the condenser is going to be 68.35 meters square. So this is a typical analysis that can be done for a single effect evaporation system. Performance ratio is still less than 1, like 0.97, which is a bit low. I mean, if you compare it with what we need for operation of a desalination system, that should be a little bit better in terms of energy efficiency. Sometimes we need to take it a little bit more here and put definitions, for example, like what's going to be the specific area. It's the total area of the evaporator plus area of the condenser divided by the product, or specific mass flow rate of the cooling water, which is going to be the mass flow rate of the cooling water divided by the mass flow rate of the distillate. How much cooling water you need per unit production of the distillate, how much area you need per unit production of the distillate. So typically, this is what you can see or what you can think of when you are considering.
Excuse me, doctor, what's going to be the temperature of vapor here? I'm a bit confused about it. Can you please tell about it? What's going to be the temperature of
Again,
vapor?
what is it?
Doctor, want to ask what's the temperature of vapor here?
Temperature of the vapor is basically the saturation temperature of the salty water minus the boiling point elevation. The
Okay,
point
okay.
here is the vapor is always pure.
Mm-hmm.
And when you are heating the seawater, if you are heating seawater at atmospheric condition, it will not boil at 100 degrees centigrade. Due to the salt content in it, it's going to boil at maybe 101 or 102 or 101.5,
Okay.
like that, because
Okay,
of the
doctor.
salt content. But the vapor, when it leaves, it will leave as the saturation temperature of pure water. So temperature
Okay,
of
doctor.
vapor, which is pure, is equal to the saturation temperature of the salt where the vapor came from, minus the quantity which is responsible for the increase of temperature due to the salinity, which is
Okay,
the
doctor.
boiling point elevation.
Okay, doctor. Thank you.
Okay. So this is basically the kind of analysis that we have for a single effect evaporation, and this is some sort of a typical kind of problem that you can see. Maybe it's worth now, because we are looking at it, is to put it like that. What are the potential wastes of energy which is not well used here? Think about it and let me know what you think is the kind of energy that we are losing to the surroundings and we are not making use of.
The cold water, which is
Can be Dr. Master Brian?
Yes, massive brine and the cold water. Yes, that's correct. We have cold water, which has been entered into the condenser. It will be heated up to TF, and then we are throwing it again. In this problem, TF is something like 70. You are throwing water at 70 degrees centigrade to the sea. This is a waste. At this temperature, we can use it for another single stage unit, or maybe an HDH unit or a membrane distillation unit, but I can make use of this water not to throw it away. The same thing applies here. You are rejecting 1.5 kilogram per second of brine to the water again or to the ocean again at a temperature of 75. That's another loss. And this is why the idea of having the multi-effect desalination came from. The point here was, although I'm not going to talk about it today, but it's just, I just want to point out the kind of benefit that we can get when we have something like this. So we have an evaporator, and from this evaporator, we have brine, which is being rejected at a temperature of 75 degrees centigrade. Why don't we get another unit here and take the brine that leaves from here and spray it here? It's already hot and you are going to spray it. Do you need additional heating? It's easy. What you can do, you can take the vapor which is leaving here to condense. When it condenses, you are going to get it as a product, and you are actually generating an additional amount of vapor here. You take this amount of vapor here into another effect and so on. And whatever is going to be rejected from here is going to go to another effect and so on. So basically, you used external steam for the first effect only. And after that, your own vapor is the source of heat for the next effect, so that you can have additional vapor, and the next effect, and the next effect, and so on. And what I'm talking about here is basically the idea of having the MED, or the multi-effect desalination. So you are reusing the vapor that you have generated, using the energy associated with its condensation to get more water and more water and more water. And that's the basic idea here. So that you are not going to throw away high temperature fluid. Maybe the temperature which is leaving here is 75. So what will leave here is going to 70. What will leave in the third one is going to be 65. And then you can continue doing that until you are rejecting energy at 40 degrees centigrade. And that's enough. I mean, if you put one more effect when you get in at a value of 40, that's not enough to evaporate additional amount of vapor to worth the investment of putting another unit with a tube bundle and so on. So typically, use like 8 effects in a system like that, so that the last effect would have a temperature that is greater than the seawater temperature by a value of 10. And you say that that's fine, this is good enough, and I have good productivity from this unit. So that actually is the idea, or the enhancement that's being done while considering improvement further on the SEE. But let's consider something else first. I'll throw the idea, I'll sketch it, And then we can get back to talk about some of the details of the components that we have here. The idea here is what's coming here. I have a single effect evaporation system, and I have a condenser here. And what we used to do is to get steam from a power plant to condense here. So it enters a saturated vapor, leaves a saturated liquid, and the latent heat of condensation is the source of energy for your feed. So I have feed here, m dot feed, which is going to be sprayed in, and there's an amount which will be rejected here, which is m dot cooling water. And the vapor is going to leave from the top here. The enhancement that we are going to do here is we need to increase the PR of the system. PR is simply m dot distillate divided by m dot steam. In order to increase the PR, I can either increase the distillate or decrease the flow rate of steam that we have. And what we are going to do now is work on reducing the m dot steam. So we are going to use a component here. The component is nothing but what we call a thermo compressor. Or ejector. In the ejector, we are going to make use of steam coming from the power plant. So the steam from the power plant will not get here, but it will be entered here. We call it m dot m, and the m here stands for motive. The motive steam that will come here is going to go through a nozzle. So when it goes through a nozzle, the area reduces. So what happens? Its velocity, hey.
Increases.
It's going to increase.
Yes, the velocity increases until the throat here, where the velocity reaches the velocity speed of sound. If the velocity here is maximum, what will happen to the pressure?
Reduced. Drop.
Will be minimum, and accordingly it's going to apply suction to take some of the vapor that we have generated. So here basically you have m dot vapor. Part of it will be entrained here, we call it m dot entrained vapor, and part will go to the condenser, we call it m dot condenser. So m dot v will be splitted to m dot entrained vapor plus m dot condenser. The entrained vapor is going to join the motive steam, and all of it are going to be mixed here. First, there's a mixing throat, and after mixing, it's going to go through a diffuser where area increases, so the velocity reduces, the pressure increases, and this actually is going to make our steam here. So I got the same quantity of steam that I wanted, but I did not get it all from the power plant. I got a part from the power plant, which is this, and a part from our own product. Did we lose this part? No, we did not. And let me show it to you. What we are having here is basically m dot motive plus m dot entrained vapor. It will all condense here. As it condenses here, after that, the m dot entrained vapor is going to join the condensate of m dot c, and then we are going to get m dot vapor or m dot d here. So I did not lose any components here. I did not lose any quantity. And this quantity of condensed m dot motif is going to go to the power plant again as saturated liquid, so that there it will be pumped, it will go to the boiler, it will go to the turbine, and then we can extract it in the turbine again right here. So the idea here is that I have reduced the steam mass flow rate, I've increased the PR of the system, and what I did is just reused some of the vapor that we are generating right here, so that we'll take it, we'll condense it here, and then we're going to make use of it at the end. Now we're going to have an example, maybe the example we can have in our next class, and you'll find that for a system like this, with the same numbers that we had today in our example, you are going to see that today we got a PR of about 0.097, isn't it? When we do that for an example with a TVC, thermo vapor compressor, we're going to have a PR that is going to increase to something like 1.47 or 1.48. So we're talking about 50% improvement in the PR just by adding this component, which is the thermocompressor or the thermo vapor compressor. This is quite effective. And as a matter of fact, the ejectors are utilized a lot in the industry. Creating vapor here or creating vacuum here or low pressure is not associated only with reducing the pressure in this area, but it reduces the temperature also. So you'll find that ejectors are having a lot of application in the refrigeration industry. Refrigeration by using an ejector. Or in the power plants, in the desalination plants, the thermal desalination plants, you'll find that the ejectors are used a lot, not as a TVC, not only as a thermo vapor compressor, but sometimes we use it because of the vacuum effect that it has. So sometimes we connect it to the units to get rid of the non-condensable gases. So we have a flow coming here, and the flow will go here. It creates suction in this area. It takes out the carbon dioxide and so on, all the non-condensable gases, and you do venting for your units this way. So they have very, very good kind of applications. Unfortunately, maybe only 3 companies throughout the whole world which is producing ejectors. We did once analysis of an ejector, and we find that the first flow efficiency of the ejector does not exceed the value of 30%. And we also found that it has substantial entropy generation associated with it. If you do search for patents that are going to be or that are published related to ejectors, you'll find many. Some of them are in Washington State University. We had a group where we did some work together earlier, and they are looking for different ideas, new ideas, where they can improve the performance of the ejector, because the better the ejector, the more the entrained vapor, the less the motive steam, and then you can have much better performance of your unit. So improving the performance, and these units are critical in operation. It should satisfy a certain condition while they are operating, otherwise they will not work fine. So there is some conditions, there's a certain range of flow rates, of pressures, of pressure ratios of the ejectors or the TVCs that should be maintained in order to make sure that it's going to operate continuously. So that was just a brief idea to some of the coming enhancements that we're going to do. We're going to do detailed analysis related to the TVC in our next class. Actually, analysis of these units remains the same. The only difference is that we have an added component, and this added component should come up with its sort of definitions and some characteristics of it, and some empirical formula we are going to do to calculate the entrainment ratio. we have something that we call the pressure ratio here, or actually we call it compression ratio, just to be more precise. So for the ejector, we have a compression ratio, which is the pressure of the steam at its exit divided by the pressure of entrained vapor. So we refer to that as the compression ratio of our ejector. And we use what we call the entrainment ratio as well. Entrainment ratio, which is basically the motive steam divided by the entrained vapor. So that is basically the kind of relations that you will be introduced to in our next time, and then we are going to combine these with our analysis here of this unit, and then we can come up with an analysis of a single effect evaporation with a TVC, which we refer to it as single effect evaporation with thermo vapor compressor. You will find that almost all thermal desalination systems are having a TVC coming with it. If you happen to drive through or close to a Ziziyad desalination system or Al Jubail desalination system, you'll find a desalination plant, and on top of it, you'll find a thermo vapor compressor. Now let's get back to our let's stop the sharing and get back to our presentation that we were considering last time for the single effect evaporation. The reason of doing that is just to have a word on something related to the components as well. So actually we have been through this last time. We talked about the objectives. We talked about the components that are making the single effect evaporation system, and the description of the system, the temperature distribution in the system. And I would just remind you now that, remember right here, we said that in the analysis of the evaporator, we have neglected this increase of temperature, and we have considered only the portion where we have constant temperature difference. If you want to do it in details, you can do it. That's welcome to take care of that. But I mean, the approximation is not bad anyway. We talked about the mist eliminator and why do we have a mist eliminator. We talked about the condenser, and we have also talked about the elements of the energy balance. And today we have gone through an example which is taking us through the mass balance, the energy balance, the performance parameters assessment, and even the calculations of the heat transfer areas and so on. So we have done all of that, and we have taken a numeric example. The performance parameters for this unit, look at this. And what we are doing here, we are changing the value of TB, the boiling temperature of the seawater which is coming in. Its temperature is being increased from 50 to 90. What is going to happen with the PR? We'll see that the PR decreases here. And when you look at this and try to find why should the PR decrease as the temperature increases, the simple explanation for this would be by just looking at this figure. What happens to the value of HFG as the temperature increases? Temperature with specific volume or with S, whatever. And what we have here basically is HFG. At higher temperature, the value of HFG is reducing. It's not reducing significantly, but it is reducing, which means that if I need to have a fixed value of Q, which is m dot S into HFG, then as the value of HFG reduces, the value of m dot steam has to increase. PR is nothing but m dot distillate over m dot steam. If m dot steam increases, then the PR decreases. Fortunately, we are lucky that the HFG is not a strong function of temperature. And that's why I look at the first two digits here. 97, 97, 97, 97, 97, 97. So the changes here is only in the fourth and maybe in the third digit every few increments. Which means that if I'm going to plot the PR versus TB, and my scale is from 0 to 1, I'm going almost to find a horizontal line. So the decrease here, yes, it is there, but it is insignificant, and here's the proof. And where it's coming from? It's coming from the fact that HFG is decreasing slightly as the temperature increases. So we may not need to go for higher temperatures. That would be the recommendation, wouldn't it be? But when it comes to the single effect evaporation or multi-effect desalination, sometimes they refer to multi-effect evaporation as well, then normally we limit what we call the top brine temperature, which is our T maximum of the seawater, to a value of 65, and we don't exceed this value. So the example that we have solved today when we started talking about a temperature of 75 is somehow of an exaggeration, and the temperature should not exceed this value. Why is that? Probably, among you, a couple of persons at least have attended this course with me before, for the undergraduate level, and they know that when we are talking about tubes that are having steam inside and having seawater splashed outside, the seawater, when it's gone outside, then the possibility of scaling would be there. And there's no way you can clean it. If the seawater is inside the tubes, then you can do like what's happening in MSF units, where you have balls like the squash ball. Normally, I have some of them in my office, they are orange in color, just like the squash ball in size, and they are not very soft, and they are admitted inside the tubes. As they are going inside the tubes, they do like rubbing or frictioning the inner surface of the tubes and cleaning the tubes from inside. So it's cleaning while operation. But for the single effect or the multi-effect, this is not the case. Spraying is going to be outside the tubes. And to avoid scaling problems, although we use anti-additives, we use like additives like anti-foaming, anti-scalant, anti-fouling components, but still, if scaling starts to occur outside the tubes, that's an additional layer of insulation, which is going to reduce the heat transfer rate. You're not going to generate the same quantity of vapor if you have a layer of insulation on the outside surface of the tube, and the whole performance of the unit would be affected. So there is a limit to the temperature, not only because the PR reduces slightly with temperature, but it is mainly because we cannot spray hot seawater on the outside surface of a metallic tube. Why is that? Because it's going immediately to result in scaling. Then some people have started working with pre-treatment of the seawater, coming with novel ideas for seawater pre-treatment, like using nanofiltration, or some of our work that we have done before, where we have a filed patent where it talks about ultrafiltration with the graphene oxide coating, reduced graphene oxide coating of the membrane, so that we can prevent the multi or the divalent ions to pass. We are just allowing the sodium and the chloride to pass, and we are not allowing all the magnesium components, the carbonates and the sulfates. They are not, because these are the ones that are responsible for the hard scaling and soft scaling. If you are going to purify your water from these components, you can increase the temperature to 85 or maybe a little bit more. When you increase it to 85, it's not because of that, But because we know that the maximum limit, if it is 65 and the lower limit is 40, then the temperature difference across the whole desalination system is 25. If you are going to have a delta T per stage as equal to 3, then you can have 8 effects only. But if this one is going to be 85, then you can have much more than that. You can have 13 effects, 14 effects. So you can produce more and more water for the same input quantity of steam at the first effect. We'll be talking about this in details when we go to the MED system, but it's just, I've been reminded when we are talking about the changes in the PR here. Look at this. We're again looking at the temperature of the boiling temperature value versus a specific heat transfer area for different seawater inlet temperature. So this is the cooling water, seawater temperature. For example, this is going to be in winter, whereas this is going to be in summer. Typically, this is what you get here in the Gulf area. In winter, the temperature of the Gulf can reach 15, and in summer, it is somewhere between 28 to 31 degrees centigrade. So the performance of the unit then is going to be a function of the seawater temperature. You can see it here. The lower the seawater temperature, the higher the area. And the higher the temperature, the lower the area. Higher temperature, lower the area. This you can see it from the expression here. Q is U into area into some sort of a log mean temperature difference. If the temperature difference increases for the same Q, then the area decreases. So you can see here as the temperature increases, and we are keeping T brine is constant. So increasing the T, we are keeping the rejected temperature, T rejected at the end, is kept constant. So increasing the temperature is going to increase the value of delta T. It will increase the log mean temperature difference. And for higher log mean temperature difference, again, the value of the overall heat transfer coefficient is higher. To keep Q constant, you need to reduce the heat transfer area. So this is why the area is higher at low temperatures. Higher temperatures, it means that area is going to be less. What about the cold side? Again, this is about a temperature difference. We are talking about temperature difference, TF minus T cooling water. This is the total area. So it has the area of the evaporator and the area of the condenser. For the condenser side, again, if the temperature difference increases, then the area is going to decrease. And that's what you see here. Okay, so for 15, which is the lowest temperature of the seawater, then this one decreases here because very low temperature of the seawater, and you need to heat it to a fixed value of TF, then the delta T is higher. Delta T is higher, then the area is lower, and vice versa. Evaporators. There is a history behind the evaporator development, which is basically, this is where the separation process occurs. This is where the seawater is coming in and the vapor is going to be extracted out of it. Then you are going to reject the brine. So the feed comes in, then it will be split into vapor that will leave condensed and collected as sweet water, and brine that will be rejected. We need to have a hot surface for the evaporation to occur, and normally steam is being used to do that. The kind of classification where the evaporators started with was basically either submerged or falling film evaporators. The one that we have been talking about a while ago is the falling film evaporator. The submerged evaporator is the old technology that was commonly used early in the 20th century. When people started to the desalination business, they were using submerged evaporators, and then because of the scaling problems, they stopped using it. Normally the tubes there's no spraying. You have the seawater in a pool, and you bring hot tubes of hot steam, and you put these tubes inside the pool. You immerse it in the seawater. So it's covered totally by the seawater, which means that you have to bring the whole body of the seawater to the saturation temperature, and then evaporation will start. It's not like when you have a tube bundle and you are spraying a thin film. Suppose there's a sprayer here, like a shower, and this shower is spraying seawater on a hot surface. A thin film is going to form here around the tube, and it's easy to heat the thin film to saturation temperature, and then evaporation will start. But if the tube is immersed in a pool, this pool is filled with seawater, you have to heat the whole seawater first to saturation, and then evaporation will start. In addition to the scaling problem that might be associated at the surface here. The surface is immersed in the salty water, which is aggressive, so you can expect scaling to occur more rapidly for this case. So what you will find here, this is the submerged evaporator. This is the pool of seawater here, which is this actually. So you have here like seawater which is coming in, and it is being stored here in this pool. And then you have the steam tube, which is the U tube here. Steam comes in as saturated vapor, leaves as saturated liquid. And then the vapor which is going to form is going to rise up here. As it rises up, it passes by a mist eliminator, which is this, which is the demister here, so that any entrained droplets are going to fall down, and it will be rejected with the brine. Whereas the vapor is going to come here, it will condense in. You have intake cold seawater coming in here, where condensation will occur on the outside surface of these tubes. And then the M dot distillate or the product is going to be gathered here, and you are going to collect it here as a product. So the idea is the same, but the way that you are making your design is different. This is the old design that we have here. And as I mentioned, the problem or the essential problem here is that you have heating steam pipe immersed in a pool of salty water. The submerged, it's fine if you don't have a problem with fouling or scaling. Otherwise, which is not actually, which means that it might not be used with seawater, because seawater is resulting in lots of fouling and scaling. And lots of chemicals need to be used to protect your surface. It needs a long cleaning time. Suppose that you need to clean the tubes, you have to shut it down. And the issue of evacuating the brine or the seawater from the unit and then taking this long tubes out for cleaning and then put it back again. So it's an issue in terms of maintenance. And the heat transfer coefficient is low. And this is one of the big issues here, because you have because basically you have like a tank here. This tank is filled with seawater, and you have a U tube here where the steam is passing in. The mode of convection outside basically is natural convection. So the heat transfer coefficient is low. Whereas if I'm going to talk about spraying case, then this is a flow over a boundary layer here. And at the edge of the boundary layer, the heat transfer coefficient is too high. And then it starts decreasing here. By the time it decreases, it leaves the tube and falls into the tube which is below it, start to build another boundary layer where the heat transfer coefficient is high. So when you look at the whole system with bundle of tubes like that, you get a value of an average heat transfer coefficient which is too high compared to the lower one, meaning that you are going to have much smaller surface area for the horizontal tube bundle compared with the immersed or submerged evaporators. Yeah, here we're talking about that's the difference. This is the one that we are using, and actually some people said, why should we make the horizontal the tubes horizontal like this? Why don't we make them just vertical? And vertical tubes is going to have a problem because if this is the tube, the boundary layer is very high here at the leading edge, and then as the thickness of the boundary layer increases, the value of H decreases. So the value of H starts high, and then it keeps on decreasing as the boundary layer thickness increases. Not like here. In this one, you have high heat transfer coefficient here, and it decreases with this boundary layer. And then the tube, خلاص, finished. You go for another one. Then high boundary layer, high heat transfer area, heat transfer coefficient due to the zero thickness of the boundary layer. So you are talking about an average heat transfer coefficient in this case, which is high, coming from this tube and this tube and that tube. That's why you can hardly find this arrangement, and the one which is dominating in the industry is this one, which is the horizontal tube system. This is the definition I was just talking about here, and the latest technology is coming with the plate heat exchangers that are going to be used, but again, having to be careful with scale formation because you are losing large number of plates and the plates are packing close to each other. So there is a problem associated with cleaning these units, that you should dismantle the unit, you should take it for clean it and then put it together again. But the heat transfer coefficient is high, and you can use like new materials which are recently developed for operation of these systems. Operation range of the plate evaporators is something like between 35 to 150 degrees centigrade for pressures of 10 to 15 bars, and the areas, they are actually modular, so you can add more tubes so the area increases, and they support high flow rates of the fluid in. Stainless steel, to fight scaling, it's a very good choice, but it has a problem that it is coming with high cost. Plastics are there, and this is something new that people are testing now. There's no issue of corrosion, but the heat transfer characteristics are a little bit less, and that's why they try to use some sort of I would say plastic alloys so that they can compensate for the low heat transfer coefficient. This is it when it comes to the single effect evaporation system. What we need to do next is to come up with the enhancement. We have already taken an example of this one, so we can move along with the next topic. But before I do that, there's a couple of announcements that I would like to make. The first one is that on Wednesday, I'm expecting like a one-page report, which is related to the project. The second announcement is, I think the homework is due also Wednesday, isn't it? Am I correct?
Sunday. I think it might be next week. 28th.
Oh, 28th, so still have time. It will be something like next Sunday.
Yes, okay.
Next Monday, I'm sorry. So Monday, is it Sunday or Monday? I think it's Sunday. 28 should be Sunday.
Yeah, doctor, it's Sunday.
Sunday, okay. So fine, I'll put it here. Okay, if this is going to be like that, so sorry. I should be ready with the graded quiz on this Wednesday, inshallah. So that on Wednesday, let's have our second quiz. And this quiz is going to be on the humidification dehumidification system. That's going to be Wednesday of next week, inshallah. The fourth thing that I would like to mention here is that the midterm has already been decided, and the midterm is going to be done on, was it 20 what? I made an announcement today in Blackboard. You might, it's on
27th.
Thursday,
It's going to be
21st.
27th March.
27th of March, yes. 20, let me check again. Yes, 27th of March. Actually, it is left. It is left to the departments to determine whether this midterm is going to be face to face or it will be virtual. So I'm just waiting for. We are going to have like a decision on that within the department. So hopefully by Wednesday I should be able to tell you how this midterm is going to be made. But anyway, it is on the 27th of March and it will be at 7 p.m. Inshallah. Okay, so now we have settled with the groups for projects, and I'm not sure about one of you who's Kazim. Are you with us, Kazim, today or not? Because he did not tell me. I just heard that he's going to, he will not continue with us in the course, but I mean, still, he did not drop it so far, and I'm waiting for him to see what he will do. Maybe he's waiting for the quiz result or so. So hopefully I'll bring it with me on Wednesday, inshallah. Any questions?
So quiz will be next Wednesday, right?
The quiz will be Wednesday of next week.
Okay.
Which will be, if today is 22nd, then in our next, it will be 3rd of March. So quiz 2, because I need the quiz to be after you submit the homework and I post the solution so that you have a look at it, and it will be on after that. So 3rd of March.
So which topics will be covered in the midterm?
In the midterm, it should be from the start up to what we are going to reach. So if it's going to be on the 27th of March, then we still have lots of topics to cover. Maybe it will cover up to the end of the MED system, multi-effect desalination.
So the final exam will be comprehensive?
Yes, sometimes we tend to take like the solar still out of the final exam. We tend to take the analytical part of the membrane distillation out of the finals, something like that. So that's something that we can agree upon on that time, inshallah.
Thank you.
Okay. Any other questions? Okay, so have you started working with the projects or not yet? Oh, that's an answer.
Yes, doctor. We are reading papers here.
Fine, okay, that's fine, because I'm going to put a deadline, and the deadline will not be the end of the semester. I mean, I'm going to have like the last 3 classes of the whole term are going to be like presentations of you groups on your work. So by that time, the work should have been done, completed, written, and the figures generated and this kind of stuff. There's one more thing, probably another announcement I'd like to do. I was going through a discussion on LinkedIn with one of the desalination experts. He got his master from KFUPM in the 80s, and he's working as a desalination expert in an RO system. So I was asking him to deliver a talk to us in the class. I told him that we have a class of thermal desalination systems, but we need to have like ideas about the RO systems and the challenge of operating them. We are going to cover it anyway in our class. Maybe I can dedicate one class to talk about the RO systems, but I needed an expert to come from the industry and talk to us about these systems. We agreed upon that principally, and maybe we can do that sometime in March, inshallah. I was also planning to call for some of our colleagues who's in the desalination industry to give us another talk and talk about the kind of fashion that people are working on today is the issue of brine management. And there have been some work in SWCC, Saline Water Conversion Corporation. And then I have one of the researchers over there. He used to be working in Doosan company who's building desalination plants, and he's working there in the research institute, and he's doing research in this area. I might be able to call him again, to call on him to give us like a talk of what he's doing lately. So I just want you to get an idea of having the principles being covered here in the classes, but we need to have some sort of a flavor of the work which is being done, either in the operation side or the research side in the industry. So this, I did not talk to Dr. M from SW so far. He's Korean, by the way, but I should be able to contact him soon. And I have one of our colleagues who's doing some of the leading work related to desalination and KAUST. I might also talk to him and ask him to give us like a 40 minutes, 45 minutes talk of his work or so. So that's something at least that when you are leaving the course, you are leaving with not only the principles that we are covering here, but you have an idea of what others are being doing around us and some of the terms that will not cover in details, like the issue of the RO. So I have this in my mind as a plan, and hopefully we can set time to do that, inshallah.
Sure, doctor, inshallah.
Okay, so if there are no questions, then you will be released something like 4 minutes earlier this time, so that I can compensate next time and keep it for something like 10 minutes more, inshallah.
Okay, doctor, no issues.
Okay, if you have no further questions, then that would be it for today. Thank you.
Thank you so
Okay,
much.
doctor.
Assalamu alaikum.
Alaikum
Thank you.
assalam wa rahmatullahi wa barakatuh.